Here are some physical properties of alcohols. Look at the boiling point. With the similar molecular weight, alcohol has the highest boiling point among all these compounds. We have alkane and alkyl halide. And the boiling point depends on the interaction, the intermolecular interaction of the molecules. And ethane, you guys know that's only London forces, so weak bond, not even a liquid at room temperature. This is gas. For chloroethane, only 12 degrees, so it's a bit higher. That's because of the dipole, right? It also got some London forces on the carbon chain. And ethanol got a hydrogen bond and a London forces, but mainly a hydrogen bonding. That's spike up the boiling point of ethanol, right? Go up to 78 degrees, right? And the hydrogen bond right there, we drew together before. Alcohol is mixable with water, and that is because the hydrophilic region of an alcohol can form hydrogen bond with water, and the hydrophobic region is small. Usually 1 to 5 carbon of alcohol is mixable with water. But once the hydrophobic region is longer than that, water start having a hard time solvating or interacting with the alcohol. Okay, just a one hydrogen bond region is not enough. You probably need to multiple. Okay, all right. Now this is important. The acidity of alcohol and phenols. Now, look at all the bases right here. All right. So which one can or cannot deprotonate alcohol effectively? If you go back to chapter 2, chapter 3, right? That's an acid and base. Acid and bases. We determine the position of equilibrium by looking at the acid on both sides. Right, so on the left side we have alcohol. The right side is going to be the conjugate acid of this guy. So if the acetate deprotonate alcohol, you're going to get acetic acid. Hydroxide deprotonate alcohol, you get water. You get all of this right here. Okay, so compare the pKa of both sides. The equilibrium will favor the side that produce the weak acid. Right, the weak acid side. So the pKa of alcohol is what? What's the number? 16. Now. Acetic acid, about 4.78 or something, about 5. Carboxylic acid, about 5. Totally go to alcohol. Let's go to the reactant, right? So we look for something that 16 or higher than 16. Gotta be higher, otherwise it won't work here. Hydroxide, so water is 15.7. No, so go backward. Ammonia. 38. Okay, let's go totally forward. That's a big forward there. Hydrogen gas, so this hydride deprotonate alcohol becomes hydrogen gas. The pKa of hydrogen gas is 35. Totally go forward. And we got alkane. pKa of alkane is 50. This guy is the strongest base known. Okay, so look for something that have pKa higher than alcohol or weaker acid, basically. Now, phenol is million times more acidic than alcohol. pKa about 9 to 10, right? So about 10 million times more acidic than alcohol. Sodium hydroxide is enough to deprotonate the phenol. Right? Look at the water, pKa 15.7, totally go forward. Right? And the reason why phenol is more acidic than alcohol because its conjugate base is really stable. They got a resonance structure there. You can draw it out. Right? Now, this equilibrium goes forward, right? Goes forward, but how much though? So let's do some calculation real quick. You don't have to do it, just want to show you. So pK of product minus reactant, so 15.7 minus 10. So you get 10 to the fifth 5.7. All right, and if you put that in calculator, it's about 5 times 10 to the fifth to the right to the product. Sodium hydroxide is totally strong enough to deprotonate the acidic proton of the phenol. Okay. All right. So we learned about that just to explain right here. So how do we deprotonate alcohol? I'm going to tell you why we want to do that in a bit. All right. But here's how. We usually use sodium hydride. That's the main one that we use. All right. So deprotonation, you get sodium alkoxide. This is ethoxide, right? Sodium ethoxide, and hydrogen gas. The sodium hydride is really common, really popular because the hydrogen gas, well, it doesn't stay in the reaction. It just float away, right? Bubble off the reaction. And the reaction is really clean. You get just one product. That's it. right? And you might see the solution right here a little bit foggy. That's because sodium hydride is reactive with even the moisture in the air. When they keep sodium hydroxide, they mix it with some kind of like natural oil or something, and when you put in a solution of alcohol, it turns foggy, so it isn't soluble that well. But the solution works. There's a lot of sodium alkoxide in here. Okay, another common reagent to deprotonate alcohol is alkaline metal, lithium, sodium, potassium. Right, the reaction passed through kind of one single electron transfer, but we're not going to do in here, and you get sodium alkoxide and also the hydrogen gas coming out too. The reason why we want to deprotonate alcohol is to increase the nucleophilicity of the alcohol. Right? And so we can use that in an SN2 reaction. Alcohol itself is a weak nucleophile. It doesn't go SN2. So we have to deprotonate it or increase nucleophilicity using this reagent. Yeah, we're going to do the SN2 of alcohol in a bit. Okay. All right, let's, one more for for phenol. Sodium hydroxide works. Just sodium hydroxide. You get the phenoxide ion. This is sodium phenoxide. Okay, all right. Let's talk about the preparation of alcohol.